Why are kinetic and potential energy tricky in thermodynamics? Have you ever wondered why kinetic and potential energy can be confusing in the world of thermodynamics? It might seem straightforward at first, but there are some key differences that can trip you up. Let's break it down together. Kinetic energy is the energy an object has because it is moving. You can calculate it by taking half the mass of the object and multiplying it by the velocity squared. On the other hand, potential energy is the energy stored in an object due to its position, like how high it is in a gravitational field. These concepts are easy to grasp when you think about individual objects in classical mechanics. However, thermodynamics takes a different approach. It focuses on the internal energy of a system, which includes microscopic forms of energy. This is where things can get tricky. The first law of thermodynamics tells us that the change in internal energy of a system equals the heat added to the system minus the work done by the system. Internal energy includes microscopic kinetic energy, like the movement of molecules, and potential energy, such as the energy in molecular bonds. But it does not account for the kinetic or potential energy of the entire system moving through space. This distinction is what makes kinetic and potential energy tricky in thermodynamics. For instance, consider a gas in a moving container. The gas has kinetic energy because of the container's motion, but that energy does not count as part of the gas's internal energy. When applying the first law, you must carefully decide whether to include changes in kinetic or potential energy of the system as a whole. If the system's speed or height changes, those energies must be accounted for separately from internal energy changes. Another point to consider is how work is defined in thermodynamics. Work done by or on the system can change kinetic or potential energy, but thermodynamics has a broader definition of work. This can complicate how energy changes relate to kinetic or potential energy specifically. Energy conversion is also an important aspect. In many real-world scenarios, kinetic and potential energy can convert into each other or into internal energy. For example, when a roller coaster goes down a track, potential energy turns into kinetic energy. If friction is present, some of that kinetic energy becomes internal energy in the form of heat. To sum it up, kinetic and potential energy can be tricky in thermodynamics because the focus is on internal energy and energy exchanges involving heat and work. Understanding when and how to include these energies in calculations is essential for correctly applying the first law of thermodynamics and analyzing energy changes in real systems.